Let's start this. Happy Monday. It's weird because I consider this our room, but then this is our last time in here. It's weird. Because my iPad's been acting up, I decided to pre-copy and paste things in. So I guess it's a little bit overwhelming, but we're just going to work our way just through basically some definitions from section 5.2. We're building up to a problem from 5.3. Now, just a couple of notes. Of course, we're supposed to introduce radians. You're probably familiar with working in radians when you're doing trig, but we're going to stick to degrees because today is our last day of material and we wouldn't get anywhere. So that's my reason for that. Okay. There are benefits to radians, right? But they're unitless. That's their kind of number one benefit. But in general, when we have an angle like this, just in terms of some terminology, we've got an initial side and then we have a terminal side. Okay? And so the angle is the measure between the two, right? And of course, this terminal side can be anywhere on a circle. We can even rotate around and around and around and around if we want to. And just as a refresher, I didn't do a very good job of lining these up last night. Oh well. So a degree is a measure of an angle, and a full circle has 360 degrees. These are all things that we know and love, maybe. So if you're working in degrees, then you should always indicate the unit, which is why we work in radians, because we can ditch the units, but that's okay. Let's see here. Hey, I need more space. So when we're talking about angles on a circle, we're going to measure angles from standard position. Now, standard position, if we are working on some axes like this, okay, standard position starts here on the positive x-axis, okay, and moves counterclockwise. Okay, and then we'll be able to have the terminal side anywhere in any one of these quadrants. Right? And so here we might have like this. But the standard position is starting on the positive x-axis and then moving counterclockwise. So of course, this arm, the terminal side, would be the same if we moved, right? If we moved from standard position all the way around and back again, right? Looks the same. Got a spiral now. And so what we call those are, we call those coterminal angles. So if two angles are coterminal, right? If they terminate in the same position. So if you end up in the same position, right? Then essentially how we're going to use this is to boil down where this terminal side is, right? We're going to reduce the full rotation. It could be 4 rotations around, but really we just want to know where is the terminal side in these quadrants. Okay. So we're going to focus on some angle theta. Now, angles are usually denoted by Greek letters. Theta is the most common, and you've probably seen theta before, but maybe not. Have you? Yeah. For angles or something else.
I just learned about it this year.
Sounds like angles to me. So we're going to focus on reducing these angles, right, to figuring out where the terminal side is on the grid. I usually just work by subtracting 360 degrees, right? Take away as many loops as you need to, right? So 400 minus 360 is what, 40 degrees? There are some kind of key points, I guess, between an angle. So this is a right angle, so that's 90 degrees. This halfway mark is 180 degrees. Halfway of the 90, I guess, is 45, just as a little cutoff point. And so on and so forth. So we can have some cutoffs and we can know approximately where the terminal side of 400 degrees is, right? So it had to go once around and then 40, right? Which is almost halfway to the 90. That doesn't make sense. An eighth of a turn. 720. I don't know. I need a calculator. Minus 360. I know that's not gonna do it probably. $720 minus 360. Hey, is 360 gonna go for 0? 840 minus 360 is 480 minus 360 is 120. Which would be roughly where, if we had to map this out. We know this is 90. This is 180. 120, I'm going to throw it. We can get more specific, right? Knowing that halfway between the y-axis and the negative x-axis is 45 degrees, right? But just for a rough idea, I'm just going to do that, right? Somewhere between 90 and 180. Negative angles do what you probably want to do. Negative, knowing nothing about it. What would you want to do? Well, if this is a positive angle, then moving clockwise would be a negative angle. Right? So here, move clockwise. Now, what is negative 60? So I want to go clockwise 60 degrees, same thing. I know that once I hit the negative y-axis, I've hit 90 degrees. So it's something less than that. Let's put it here. Negative 60 degrees. Making the coterminal angle (300 degrees). Since a full circle has to be 360, so if I've moved kind of backwards 60, then I have to go forwards 300 to meet in the same terminal position. How about negative 500? You can do the same thing, just remembering that you're moving clockwise now instead of counterclockwise. So if you have 500 minus 360, you get 140. I guess plus 360 in this case. So negative 500 plus 360 is negative 140. Negative 140. Where can I put this? Tiny. I know if I go from here all the way over here, that's negative 180. And if I go to the negative x-axis, that's 90 or negative 90. So then negative 140 is somewhere kind of in here. And we can get more precise, but it's not terribly important right now. So negative 140 degrees is going to be coterminal with 360 minus 140, gonna go for 220. Just make sure that they add up to 360 and kind of cancel each other out, so you end up in the same spot. Okay. So even if you have these crazy large angles, you can reduce them to something just on the circle. If you have a circle, right, starting here in standard position, then the arc length of some arc S, right, the most basic arc length that we know is the circumference, right? That's the entire arc length. Now we're talking about a portion of the arc length. So the circumference, the overall circumference, the total circumference is 2 pi r, where r is the radius. And so now we want to find a portion of that 2 pi r, depending on what r is and what theta is. So if we have a circle of radius 6, then r is 6. We want to find the arc length of a quarter rotation. Right? So the arc length of from here to the positive y-axis, that's a quarter rotation. Right? How would you approach this? If we know the total circumference is 2 pi r, right? You could find this entire distance, 2 pi r, knowing that the radius is 6, and then cut it in quarters, right? Each of these quarter distances are going to be the same, so we're allowed to do that. So if we have the circumference is 2 pi r, then we get 2 pi 6 or 12 pi. That's the full rotation. Now, if we want a quarter rotation, is 1/4 times 12 pi. I'm going to go for 3 pi. That's the arc length. Uh-oh, I forgot to cut one thing. Radians. 12 pi divided by 4. Now you got me second guessing myself. I was feeling confident. The radian measure is a ratio of the arc length but, and the radius, but we're skipping it. And I should have cut it. It exists, it's a big deal, but we're skipping it because it's our last day. And I want to be able to solve some problems. Okay. Hopefully we can do this one. So if a person walks 140 degrees around a circle with a radius of 50 feet, how far do they walk? Something like that. That's actually not. Forcing the radius to be 50. First, to visualize it, let's figure out where 140 degrees would be. All right, just to figure out roughly what we're looking at. I know that this point is 90 and this point is 180. And so I'm going to go somewhere in here, maybe. .140 degrees. We can find the total circumference. All right. And then what can we do? We can take only 140 out of 360 of that circumference. C is 2 pi r, which is 2 pi times 50, which is 100 pi. So this distance here is 140 out of 360 times the circumference. So the distance, 360 times 100 pi, my calculator says 350 over 9 pi is the exact answer. But let me, oops, 350 pi divided by 9. What's the distance? Roughly 122.1730476 feet. Roughly. You can leave it exact if you want. Nice. Mostly because our calculators just do it anyways. Good. Questions, comments, concerns? So far, so good. Nice. All right. 5.3. So we got kind of what we needed out of 5.2. Right? They talk about degrees or radians and converting between degrees and radians. And I said, just going to use degrees. And with that said, make sure your calculator is in degree mode. So on most of the screens, there's a little D highlighted at the very top. If there's a little R highlighted, we'll need to change that to degrees for this class. All right. It's possible that in physics or whatever other course you're taking should be in radians. So just make sure you switch it to degrees for us. Okay. So in terms of sine and cosine, SOHCAHTOA coming up here. Got this. So for some point, xy, so any point on a circle with some radius r at some angle theta, what we can do is we can make a right triangle in here, right? This becomes a right triangle, where I have 90 degrees. If I drop down from the point, I can figure out the y point, right, by figuring out how far off the x-axis it is, and I can figure out the x point by figuring out how I want to say deep, how far into the x-axis it is, right? And so if we drop these points down, then we get this right triangle. Now, the sine of theta, and of course your calculator just calculates sine of whatever angle you give it, right? And so that's where it's important that you have it in degree mode. And y, right, is the opposite of theta, right? So here, this is opposite of theta. I guess I could. So y is the opposite. R is the hypotenuse. Right. So r is the hypotenuse. So opposite over hypotenuse, which gives us the familiar sine is opposite over hypotenuse of SOHCAHTOA. I feel like I've heard a weird take on SOHCAHTOA, but I can't remember what it is. But hopefully SOHCAHTOA is what you're familiar with. So then, of course, if theta is here, this is the opposite of theta. This is the hypotenuse because it's the longest side. Then this is going to have to be the adjacent. Also because it's adjacent to theta and not the hypotenuse. And so here, this is the adjacent. So then x is the adjacent over the hypotenuse, which is the cos is the adjacent over the hypotenuse. If you wanted to solve for the points x and y, so figuring out what point on the circle from some theta, right? So I give you a theta, what point is on the circle for this terminal side, right? Then what could you do? You could rearrange these, right? You could solve for y by multiplying r over to the left-hand side. So then y is r times sine theta. It's easy enough. Solve for x by multiplying r over to cosine. So then I have x is the cosine of theta times r. They're in here, that's why I didn't write them down. So on a circle of radius r at an angle of theta, we can find the coordinates of the point at that angle by using x is r cos theta and y is r sine theta. You can get there just from the, well, we're going to focus on the SOHCAHTOA, ditch TOA even, you can believe that, but you can find the tangent, but we're going to focus on x and y. On the unit circle, we know that the radius is 1, right? And so then r is 1, so then x is the cos of theta and y is the sine of theta. Let's see here. I'm gonna shrink this down, put this down here. clean up a little bit. So if we have a circle of radius 5, then there's a point 3, 4 on that circle at some angle theta. We want to find cos theta and sine theta. So what we want to do is first sketch out the scenario. Oops. Now for us, we're going to only work with circles centered at the origin. And if I want to find 3, 4, then I've got 1, 2, 3 on my fake scale. And 1, 2, 3, 4. It's not to scale, obviously. But just to get an idea of what I'm expecting for my angle, right? What does this tell me? If my point on the circle is in this first quadrant, this is the first quadrant, second quadrant, third quadrant, fourth quadrant, I'm expecting this angle to be between 0 and 90 degrees, right? I can get a little bit better of an idea, right? I don't expect it to be quite 90 degrees. I expect it to be somewhere between those 2 points, but just as a way of checking your work, right? Then let's see here. We're also going to force the radius to be 5. And then I'm going to draw my circle here. Close enough. And then this, wait, this is theta. So just working with the so and the ka, right? We could jump right in and say, okay, if I know that x is 3 and y is 4, I know the radius is 5, then you can solve for sine and cosine, right? But what if you don't see that right away, right? That's totally fine. Just go for it. Then what would you do? You'd say, okay, well, let's start small here. I can drop this down, and I know that this is 4, right? Because the y value is 4. I know that this distance is 3. And I also know the hypotenuse is 5 because the radius is 5. So now, from here, I can say, okay, if I want the sine of theta, the sine of theta is going to be the opposite, which is 4, over the hypotenuse, which is 5. How do I get that theta? We haven't introduced it, I'm realizing now, but you can take the inverse. So sine inverse is a button on your calculator. Yeah, right? Where is it? Yeah, so there's a sine button. So here, first, I'll just clarify. Now, to solve for theta, use sine inverse of 4 over 5. And let's see here. I'll use this calculator. What? up. Come on. Just doesn't want to behave today. So first thing, you want to make sure that you're in degree mode. Because we're going to work in degrees. And then if you want to take the sine of some angle, then you would press sine, and then presumably on mine, which is slightly different, it does sine bracket and it just wants whatever you want the sine of. But we're focusing now on the inverse. Now these are the inverse functions. So if you want the inverse sine or sine inverse, you'd have to go shift sine inverse. So let's do that. Copy. I drew over it. Oh well, I think you get it. So then sine inverse of 4/5 in this case. 4/5, close the bracket. I get roughly, theta is roughly 53.13 degrees. First thing you want to do is make sure, does that make sense? It does, right? I was expecting my theta to be somewhere between 0 and 90 and kind of closer to the halfway mark. So 53.13 degrees makes sense. Let's confirm, because we wanted to find the cos of theta. Actually, oh, I guess I see what I did. I thought, hey, that's weird. Why am I taking it into the inverse? I wanted to, I just didn't think we would. It's because they only wanted us to find cos theta and sine theta. Sine theta is 4/5, so then we would be done. But I want to take it another step further here. Solve for theta and solve for theta. Why not? We can do it. And we did. Let's find cos theta, right? So we worked on sine theta. Let's work on cos theta. And we can do the same thing just to make sure that we get the same angle, because it should be, right? And so now if we work on cos theta is the adjacent over the hypotenuse, so 3/5. Technically, that's the answer that it's all we wanted, right? But in order to solve for theta, theta is the inverse cos of 3/5. Shift cos inverse 3/5. Really hope I get 53.13. Oh, phew. Degrees. Nice. Any questions about that one? Yeah. 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 So if you have x is 3 and r is 5, then cos theta should be 3/5 once you divide over the r. But this is just a special case, or like a rewritten case of this one. So this one's really the only one that you need, right? It just depends on if you want to solve for x and y, then it's nice to have them rearranged already. But nice. Okay. The Pythagorean identity says that for any angle theta, cos squared theta, which is just the square, plus sine squared theta is 1. Yeah. So we can use that. I was going to develop. No, we'll just use it. So if we know that as a fact, cos squared theta plus sine squared theta is 1, then we can find sine theta if cos theta is 5/8. Wow. Now these squares behave just like normal squares. Normal powers of 2. So then if I have cos squared theta plus sine squared theta is 1, but I know that cos theta is 5/8, then 5/8 squared is cos theta squared plus sine squared theta is 1. 5/8 squared, 5/8 to the power of 2. Nice try. Okay, it doesn't really simplify to anything nice. 25/64 plus sine squared theta is 1. I can subtract 25/64 from both sides, 1 minus that little guy. I get sine squared theta is 1 minus 25/64. So sine squared theta is 39/64. That's from my calculator, but you could also say, okay, I need a common denominator of 64 here. So this 1 turns into 64/64. 64 minus 25 is 39. Bada bing, bada boom. Now to get sine theta, I can take the square root of both sides. And the square root of that little guy is the plus minus the root of 39/8. If cos theta is 5/8, right, then where are we? Here. Then I have, so cos is adjacent over hypotenuse. And so if I have some theta here, then I've got 5 and 8. So we could have solved it this way by saying, okay, if I know these two sides in a right triangle, I can solve for this side. But also what I'm trying to get at is that, okay, if 5/8 is in quadrant 1, So cos theta is in quadrant 1, then of course sine theta has to be in quadrant 1. So we were given two options here, right? But my sine theta has to be positive. Right? And so in quadrant 1, sine theta, whoops, is positive. Therefore, the root of 39 over sine theta is the positive root 39 over 8. How else could you have solved it? Call this y. Then we know from the Pythagorean theorem that 5 squared plus y squared equals 8 squared. So 8 squared, where is it? Minus 5 squared, 64 minus 25. Well, wouldn't you know it? Y squared is 39, so y is plus minus the root of 39, right? But again, in quadrant 1, y is just the root of 39. So now the sine is the opposite, which is root 39. The opposite, root 39 over the hypotenuse 8. So two different ways that you could solve it. You only have to do one, obviously, but whichever way you prefer is fine. Maybe this way is easier. Either way, you're using the Pythagorean theorem just in different capacities. And that's how they are related. How about a word problem? I know you guys love those. Start on a fresh page here. A boat is detected by radar 8 miles away at 70 degrees north of east. Well, I'll get you started and then I'll give you a little bit of time to try it. What's the key here? Knowing what 70 degrees north of east is saying. Okay. So here we've got north, never eat shredded wheat. And so a boat is detected by a radar. Now I'm going to say the radar is here at the origin because that's the only way that this problem makes sense, even though it's not clear necessarily, I guess. But 70 degrees north of east. So I'm going to force this angle to be 70 degrees north of east. And 8 miles away. So here's our boat. Can I draw a boat? No, I can't. It's just a little sailboat. And this is 8 miles away. How many miles north, so on the y-axis, and east of the radar is it? Some time to work on it, think on it. Maybe not yet. Work on y first. There's lots of different ways that you could solve it, right? Let's stick to our go-tos. SOHCAHTOA. So if I have the sine of 70 degrees, because I have my angle, then that's the opposite over the hypotenuse, which means that y over 8. So then y must be 8 times sine 70 degrees. Or you could have jumped straight there from y equals r sine theta if you wanted to, but I just skipped that. Now, 8 sine 70, making sure you're in degree mode. Start with the sine 70 times 8. I get roughly 7.517540966. Which means it's roughly 7.5 miles north. How about x? Same deal, right? I see that I'm trying to solve for the adjacent to 70 degrees. So I'm going to leverage that and say that, okay, cos of 70 degrees is adjacent over the hypotenuse, so x over 8, which means that x is 8 times cos 70 degrees. Cos 70 degrees times 8, x is roughly 2.736161147. 2.7 miles, roughly. The boat is roughly 7.5 miles north and 2.7 miles east of the radar. Yeah. I don't think I have another. No, no, no. Be boring to do another boat one. I don't have another example up my sleeve. I never thought we'd get here, actually. Can it be a boat? A canoe. That's so different. Thank you. Love it. Instead of a radar, how about a lighthouse or something? Huh? A canoe is, let's say, 4 kilometers. Wow. 4 kilometers away from a lighthouse. What was the structure? I'm gonna go for 40 degrees south of west. Oh, rude. And then what was it? How many kilometers? South and west is the canoe from the lighthouse. So similar yet so different. You can tell it's a canoe because it's longer. Doesn't look very good. Oh boy, a lighthouse? Ugh. It's a lighthouse. Same question, similar, except where are we gonna take this point? Oh, and I guess it was 4 kilometers away. Now this is my y, which is technically going to be a negative value, right? Because it's going down from the x-axis into the negative y-axis. And here, this is going to be my x, which is also technically negative, right? Going into the negative x-axis. Now, those are just distances, right? But when we're looking at it, it helps to remember there. Same deal as before, though. Once you have a right angle, right, then we can just solve for this, right? I can take this triangle, I can put it on its side if you want, right? And then just look at it that way. But regardless, this is your theta, which is your 40 degrees, right? And let's start by solving for, you know what, let's get wild and crazy. Let's solve for x first. Nothing holding us back. The cosine of 40 degrees is going to be the adjacent x over the hypotenuse, which is 4. So x is going to be the cosine of 40 times 4. I get roughly 3.064177. It's actually not repeating, but let's go 8. Notice that it's in the negative direction, right? So if you were doing just regular math, right, then that would matter. But for us, right, 3 kilometers is 3 kilometers. There's no negative 3 kilometers, although technically, I guess that's what it would mean to the west. Right. And so here, on the negative x-axis, so x is roughly negative 3.06 kilometers. Or should we just get really sloppy on our last-ish day? 1. How about solving for y? Y is the opposite of 40, and so I have the sine of 40 degrees is the opposite over the hypotenuse, which is 4. So y is roughly sine of 40 times 4. 2.571150,439. On the negative y-axis, approximately. Oh, this is gonna hurt. Y is roughly 2.6, but negative. 1 decimal place? Come on. Which means, right, moving south is moving down, right? So 2.6 kilometers south and 3.1 kilometers west of the lighthouse. Therefore, the canoe is 3.1 kilometers west and 2.6 kilometers south of the lighthouse. Ta-da! I guess I could do another one with a paddle board, but I think you get the idea. A paddle board and a buoy. Boring. Where would I put it? I only have so many options. I guess I have 360-ish options. I think that's good. Look at us. Ending early on our last-ish date. So on, yeah, question? Homework question, yes. Let me just, so on Wednesday, I want to do an overview for the final exam. And so just to give you an idea of the types of questions, how many points per part, section, that kind of thing. And then with a little bit of luck, I'll have the practice final done. But it's, right now it's not looking good. But we'll see if I can pull it off. But I'll try to put together some practice problems, some kind of key practice problems. But you've been tested on everything except for the last part of exponents and logs, right? Where we did those word problems, and now it's escaping me what they were about. There was one quite long one that we did. Pretty fun. And then we moved into circles, right? And so that's new. So, but otherwise you have practice material. And in terms of the final exam, I'm only going to test those types of problems that you've seen on a previous test. Okay, so you can use the practice for those tests, right? Because they gave you an overview and how to prepare for each test. And then just from those tests, I'll pull some key players, right? And that'll be your final exam, including this new stuff, right? Circles, more complicated logs, and how about a paddle board and a buoy or something? Now, question. Yeah, that's the tricky one.
Yeah, it was that earthquake one, but I had 400 times more energy. And then I looked at your example to kind of follow up, because it wasn't a simple 10 times more energy as a log 10, it was 400. So I'm like, what do I do? And I sat there for an hour scratching my head, trying all different ways.
Can have a look.
Yeah?
Yeah.
Okay.
Any other questions? All right. Then I will see you Wednesday for some review-ish, sort of. Overview.